Section 15.2 in Chapter 15 of our textbook introduces what's called ratio control. Ratio control is very common in chemical and biological manufacturing processes. Ratio control essentially controls the ratio of two process variables. Usually these are flow rates. It may be that the ratio of the two flow rates is important in a blending operation to achieve the desired composition. It might also be that the ratio is important for controlling reaction stoichiometry. For example, the air-to-fuel ratio in a combustion, or the acid-to-base ratio in a neutralization. Ratio control is also sometimes used in separation operations. In what our textbook calls Method 1, the two process variables being ratioed are both measured. In this case, it's the flow rate of two streams, one called D, which is the disturbance, and one called U, which is the manipulated variable. These two flow rates are fed to a divider element to calculate the measured ratio, and then that's compared to a ratio set point at a ratio controller. It's important here to note that dm and um are physical process variables and not the deviation variables. If these were the deviation variables, they might be very close to zero, and we would not be calculating the ratio, we would be calculating the ratio of the deviations. Method 1 has a couple of disadvantages. One disadvantage is that a divider element must be included in the control loop. Another disadvantage is that the process gain is nonlinear. Remember, the process gain tells how the controlled variable, which in this case is the ratio, is affected by the manipulated variable, which in this case is the flow rate U. The process gain is 1 over d, and since we're assuming that d is varying with time, since it's our disturbance variable, that process gain is not constant. A non-constant gain means that the relationship between the manipulated variable and the controlled variable is nonlinear. Now, if the deviation in d is a small fraction of a very large number, then we might approximate the process gain as a constant. But on the other hand, if the deviation in d is a large variation in a small number, then Kp would be changing with time. The second way of implementing ratio control, what our textbook calls Method 2, measures the disturbance and sends the disturbance to something called a ratio station, where it's multiplied by the desired ratio. The result of d multiplied by the desired ratio is then used as a set point for a flow controller, which in this case manipulates the flow rate of the second stream. In this case, the process gain is linear, but one disadvantage of Method 2 is that the ratio is never actually calculated, even though the flow rate of both streams is being measured. Summarizing what we talked about from Chapter 15, feed-forward control can compensate for known disturbances, minimizing their effects on controlled variables. Feed-forward control is usually combined with feedback control, and this combination can be achieved in various ways. The reason we combine feed-forward control with feedback control is because feed-forward control cannot by itself account for unknown disturbances. Feed-forward controllers can be designed based on either steady-state or dynamic process models. Feed-forward controllers can be tuned to improve their performance, and they can affect the stability of feedback control loops depending on how they're coupled with feedback controllers. If we use feed-forward control with feedback trim, where the signal from the feed-forward controller is added to the signal for the feedback controller before going to the control valve, then the feed-forward controller does not impact the stability of the feedback control loop.